let's talk about conditional expectation. So, how do you change your expectation? How do you update your expectation when new information arrives? And we'll work with an example. So let's look at, if you pick a random person in the US, what will their height be? So we're interested in the random variable height. Okay, and if you look at the PDF for the height, maybe you'll get something like 55 inches if you pick a random adult. Okay, 55 inches is, let's say, the minimum. Let's say 80 inches is, let's say, the maximum. And it's going to have some distribution, okay? And you might think it's going to be some kind of a bell-shaped distribution. Actually not. It's a little bit flatter than a bell-shaped distribution. Okay, and if we ask what's the expected value of the height, so the expected value of the height for this random experiment, so each value of the height has some probability. You take each value, weight by the probability, and compute the expected value of the heights. Okay, and we can get this kind of a distribution from various kinds of government census data and biological data and so on and so forth. So we can compute the expected value of the height, and it's approximately 66.5 inches. Okay, and it's not expected bell-shaped distribution that we are used to seeing when we do things in practice. Okay, and why is that? It turns out that it's because the population is composed of men and women. Okay, so let's now give you more information. Supposing I tell you that the random person is a man. Okay, so the random person is a man. Okay, what about if I told you the random person is a woman? The random person is a woman. Okay. So, if I tell you that the random person is a man, then, the distribution, the PDF of the heights changes. And so you have the probability that your height equals X given man, and you'll have the probability that your height equals X given woman, or male, female. Okay. And if we look at these two PDFs, and the overall PDF is in some sense a sum. It combines these two PDFs. If we look at these two PDFs, we indeed see something that looks like a bell-shaped curve. So the PDF for women looks something like this. Okay, so it's a bell-shaped, this red distribution that I've drawn. And the PDF for men, the distribution of men's heights. Okay, so the PDF, the probabilities for various heights for men is similar, but it's slightly shifted to the right. So it looks very similar, but slightly shifted to the right. So you get, something like that. So it's again another sort of bell-shaped distribution that's slightly shifted to the right. So whenever you see in practice, something is not having this bell-shaped distribution, and we will not discuss the theory of all this, but if it's not having this bell-shaped distribution, if it's a little bit flatter than a bell-shaped distribution, usually that means that there are two phenomena going on. In this case, there's the heights of the women and the heights of the men that are slightly offset. Okay, now, we can ask, if the random person is a man, the expected height is slightly higher. Okay, so the expected height given man is slightly higher. It's approximately equal to 69 inches. Okay, so it's slightly higher than the average among all people, and the expected height given woman is slightly lower than 66.5. It's approximately equal to 64 inches. Okay, and so we might ask, well, what's the definition of the expected height? So the expected value of a random variable, okay, given some information. So for example, that your outcome belongs to the set man, or your outcome belongs to the set woman. So we update the PDF to take into account that information, and then we compute the expected value in exactly the same way. So the expected value of a random variable x, given some information A, that the outcome is in a set A, is exactly equal to the sum over the possible values of x, okay, in, x of omega. So the possible values of big X, possible values of x, okay, times the value weighted by the probability of x. But that would just be the expected value. No, you don't weight by the probability of x. You weight by the probability that x equals my little x given A. So this is the conditional PDF. That's the only change. This is called the conditional PDF. So I'll write that down. I'll summarize that here. So the expected value of x given A is equal to the sum over the possible values, x in x of omega of x times the probability distribution function for x given A. So, you compute conditional probabilities and then weight the possible outcome by conditional probabilities and then sum and you get the expected value. Because when you update a probability, that's what you do. You update a probability. So you're computing the expected value with respect to the updated probabilities. So this is the conditional, what's called the conditional expectation. Okay, and I'll box that. Got lots of boxes here.